Hi, in this video I will talk more about transformations of the response variable in an experimental design. The video will cover when and why we need to do a transformation of the response and what we are trying to achieve with this transformation. I will provide some common examples of transformations. We will look at the Cox plot, which is a tool to choose a proper power transformation of the response. And we will also look at some of the help that you can get from the software that you use. Uh, the need for a transformation usually comes when we learn that there is something strange with the model assumptions, or the model assumptions are not fulfilled. And in order to do that, normally we have to look at the residuals, which is the actual recorded value in the design minus the predicted value from our model. And we know that residuals in the model assumption, we know that residuals should be normally distributed, independent, they should have expected value 0, or in Swedish väntevärde 0, and constant variance. And this is sometimes summarized as NID 0 sigma squared. So the basic idea with a transformation is that if our model assumptions are not fulfilled, or for that matter, if the model fit to the data is not good, we can try to see if we can improve the situation by transforming the response. So instead of y, we will use a transformed response, and let's call it y star here. And this transformation can be decided in different ways. More on problems that may cause a need for a transformation. We can have data and or residuals that are not normally distributed. That's not uncommon. So we can try to transform the response in such a way that the distribution of the data gets closer to the normal distribution. Residuals may also not have a constant variance, so we'll try to use a transformation to stabilize the variance. And we also have some situations where the data is assumed or can be assumed to come from a distribution where we have known standard transformations that are expected to work well. And then we can try one of those standard transformations to see if this fits or if this improves the situation in the residual analysis. Here you have a table with some standard variance stabilizing transformations. And this table is also given in the course book. So this table, we can see sort of the connection between the variance or the standard deviation or the variability of y and the expected value mu. And we have the suggested transformation and some comments here. So if the standard the standard deviation of y is constant, well, there is no need for transformation. Uh, if the standard deviation of y is proportional to the root, the square root of the expected value, then the square root can be used. So the transformation is to use the square root of y instead of y. This is a common transformation for Poisson distributed data, and so on. So you have a couple of standard variance stabilizing transformations dependent on how the connection between the variance or the standard deviation of y and the expected value is. There are other known standard transformations also. Here you can see the type of data we have, the type of response variable we use, and the suggested standard transformations that has been proven to work well. So for example, if we use variance or standard deviation as a response, we should almost immediately think about using the logarithm instead of the original y values. So instead of the variance, we will use the log of the variance, for example. And as we just said, for Poisson distributed data, such as a count of number of faults per unit or per product, we can use the square root transformation. And for binomial data, which can be like a ratio between 0 and 1, such as a ratio of non-conforming products, we can use the arc sign of the square root, which is a little bit peculiar looking, but it has been proven to work well. Okay, so the box-Cox plot and the power transformations. The power transformations is it's a useful family of transformations, and we can consider the power in this case to be lambda. So we will use the transformation would be y is equal to y to the power of lambda. And the box-Cox plot can help us to find an optimal value for lambda. But in practice, there are some simplifications made. So for example, if we get an optimal lambda value of 0.58, for example, it's quite close to 0.5, which is the square root of y. So instead of using y to the power of 0.58, it makes some sense to use the square root instead, to make it a little bit easier to comprehend also and to explain maybe. The software will also give you an interval for lambda, a confidence interval, and if the confidence interval includes 1 is y to the power of 1, which is actually no transformation. So if the confidence interval includes 1, then there is no transformation recommended by the box-Cox plot. So let's take a look at the box-Cox plot in Design Expert. Here you can see the current lambda is 1 because currently we have no transformation. The best lambda, the optimal one, is 0.8. The optimal one is the lambda value that minimizes the natural logarithm of the residual sum of squares for the model. And you have the confidence interval limits here, and you have a recommendation which is none. There is no recommendation to perform any power transformation because the value 1 is within this confidence interval. Okay, and then let's quickly run through some help that you can get from the software. When you come into the software, you will have in the analysis part of the software, you have this first pane, which is the transformation pane. And here you have a couple of important you have important information to read. For example, this that if you have a ratio greater than 10 between the maximum and the minimum value of the response, that usually indicates that the transformation is required. And that for ratios less than 3, the power transformations have little effect. And in this case, the specific case, this example, we have a ratio of max to mean of 1.93, which is less than 3. So probably we will not have so much use of a transformation in this case. And you have the options here, like standard transformations. You have none, the square root, the natural log, the base 10 log, inverse, square root, inverse, power, logit, and arcsine square root. And let's quickly run through, and you will see that if you, for example, are considering the square root, you have some help text here, like use when the response is a count. And this explains a little bit, maybe untransformed data, what kind of pattern you may be looking for in the residuals versus predicted plot. If this happens, then maybe the square root may be a good transformation for this behavior. And you see here, maybe this is a little bit more severe. You have the natural log here. use when the response is a variance or growth data, for example, and so on. And we can quickly run through the next two. You have the inverse square root when the response is a rate. You have the inverse when the response is a rate. So there's two versions of that to solve that problem. And then you have the power family, which is also part of what you get from the Box-Cox plot, or the recommendation you get from there. You have the You have the Logit, which is useful when the response is bounded by a lower and upper limit. And you also have the arcsine square root, which is also often useful when the response is a proportion or a ratio between 0 and 1. Yes. So the message here is to read the help text in the transformation pane, try to get a feeling for the different transformations that are available and in which cases these transformations are useful. But also remember that, at least I think it's valuable to do the transformation, do the transformation after you have looked at the diagnostics pane. So you may fit your model maybe with untransformed data. You look at the diagnostics, you have a transformation in mind. If the diagnostics look really good without the transformation, then maybe there is no need for a transformation. But yeah, so you should work with the building your model, looking at the diagnostics, going back to the transformation pane, building your model, looking at diagnostics, and so on. Try to get a potentially improved situation by doing a transformation. Okay, to sum this up, some important parts in this video then. You should be aware of why we may need to use a transformation of the response, how this works in general. You should be familiar with standard or typical transformations. You should be able to understand the Box-Cox plot and how that works, and also the possibilities in the software for transformations, which can be very helpful for you when you are analyzing the designs that you have. Okay, with that I will conclude this video, and I thank you so much for listening. Bye bye.